Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let's just jump into it. Okay, there we go. All right, so we are looking at yesterday's lecture. Let's just do a very quick recap. We have spent it on, well, a little more than half, on trig substitution, all the variations. And we looked at, well, the important thing for trig substitution, as you might recall, is this table right here, which tells you the kinds of expressions that you can use a trig substitution on. It has to be like constant squared minus x squared, a squared plus x squared, or x squared minus a squared. And here x represents a variable, which it could be something else. It could be like an x plus 2 or something like that. But once you have this kind of idea, there's a variable component squared minus a constant squared. And you can actually apply, as you can see there in the middle columns, sorry, got distracted by a message here. So you can just use the substitutions in the middle column to actually transform the integral that you're looking at into a trig integral, where you can actually use trig techniques to do it. Once you've done that, the last column here, the one on the right that's in green, kind of tells you how to construct triangles so that you can do the back substitution. You can figure out what your original variable, what functions in your original variable would replace whatever trig functions are in your answer. And by doing that, we can solve a lot of integrals that we couldn't solve by other means. So for example, this guy right here, everything that we've learned before up until this point, couldn't really handle that, but with a trig substitution, we got a relatively simple trig integral, which we know how to deal with. And so that is the idea. Once you make these substitutions, you follow through like a regular substitution. You say x equals something, you're gonna have to find the dx in terms of a d theta, you're gonna swap things out. And the idea is that integral is going to end up being something else that you can figure out. And once you have their answers in thetas, you can use that triangle to convert the answer to the original variable. One recommendation is, if you're given a definite integral, you don't want to go through the back substitution because that would end up wasting some time. So I actually saw that with this example, right? So definite integral means you have numbers on the limit. So in this case, these were radical 3 and 2. These were limits on our integral. And whenever you see that, and you know you want to do a trig substitution, I would recommend that you change the limits. So just do these calculations and to figure out for those particular values of x, what would your theta be? Generally, that's going to be easy to figure out because it's going to be values from that table I had you guys memorize in like lecture 1. And you can actually change the limits. So the limits here went from radical 3 and 2, and they ended up being 0 to pi over 6. Now, the benefit of that is once we get an answer in terms of thetas, we can plug in these numbers directly into that function. We do not have to go through this whole thing of converting a bunch of stuff and then plugging in x's later on. That actually takes a little bit more time. So changing the limits whenever you have a definite integral is to your benefit. Anyway, we did a bunch of examples on trig sub, and realize that sometimes completing the square is useful because, again, you need it in one of these 3 formats, right? Like an x squared minus an a squared, x squared plus a squared, or a squared minus x squared. And we did a bunch of that. Then we spoke about when to use a trig sub versus not using a trig sub. And basically the rule of thumb was, all right, if you have an odd powered factor of x elsewhere other than your substitution, a regular substitution should be able to work. If you have only even powers, then you would need a trig sub, generally speaking. And we're actually going to talk about that a little bit later on. And it doesn't only mean odd factor in the numerator, odd factors in the denominator, like this example here, can also work. However, in cases like that, you might actually need an additional technique, which is the one I'm showing you now, which is partial fractions. So we didn't really do anything with partial fractions. We kind of learned about the background that you need to be able to perform a partial fraction decomp last class. So partial fraction decomposition. This is the idea of taking a big fraction and break it down into smaller fractions where those fractions are easier to deal with. And there is an entire strategy for being able to do that, as well as some conditions for when it is possible to do this in the first place. So you remember, you have to have a rational expression that is proper, meaning the degree of the numerator is strictly less than the degree of the denominator. If this is not the case, you can actually make this the case via something like long division or algebraic manipulation. Once you have that, though, you can go through these, well, that and the denominator needs to be factorable. So once you have that and you factor the denominator, you can go through these steps to actually create the partial fractions. And we looked at those steps. So algebraic manipulation, this was just to transform something into proper that wasn't proper, or long division. And so the basic idea, which we're going to do more of this today, but I just want to run through it for you. So let's say you have a proper fraction, the denominator is factored. How do you continue? Well, you break up that big fraction into smaller fractions based on the factors in the denominator. So in the first case, for example, you had the denominator was x times x plus 2. One factor is x, one factor is x plus 2. You would break that into two generic fractions that look like fractions with the denominators x and x plus 2. The numerators are some generalized generic numerators that we put on that we need to figure out what the coefficients are so that the two guys on the left will, the two guys on the right will add up to the guy on the left, right? So in order to get that done, whatever we have in the numerators must be 1 degree less than the denominator. So if your denominator is a quadratic, that cannot be factored any further. Your numerator needs to be linear. If your denominator is a cubic, your numerator needs to be a quadratic. If your denominator is a linear function, your numerator needs to be a constant, etc. You always go 1 degree less. One situation in which this rule is still applied, but visually it might look like it's not being applied, is whenever you have a repeated factor. So for example, here with this expression here, the x plus 1 factor, which is a linear factor, is repeated. It's actually multiplied by it twice. So what you do with that is you count up to the multiplicity, right? So you start with x plus 1 to the first power, x plus 1 to the second power. If it were a cubic, again, you count up to that, x plus 1 to the first power, x plus 1 to the second power, x plus 1 to the third power. And the numerator still takes 1 degree less than the inner factor, right? The x plus 1. So because the x plus 1 is linear, your numerator needs to be a constant. And we actually looked at why that was. And once you actually have that breakdown, once you're here, the goal would be to be able to find what these constants are. What would a and b have to be in order to make this equation true, right? And we saw two main methods to actually get that done. One, and they both actually start the same way. Multiply both sides by the denominator on the left. You'll get an equation where there are no fractions anymore. And one method is to just plug in some convenient x values. Plug in values where you can eliminate some of the expressions, where you can get to solve for the remaining ones. So in this case, if I plugged in x equals 3, that would kill the b expression and I can solve for the a expression. If I plug in x equals 2, I kill the a expression and I can solve for the b expression. And that way I can actually figure out that this fraction 1 over x minus 3 times x minus 2 is actually equal to, 1 over x minus 3 minus 1 over x minus 2. The second method, again, you start off with the same way. You clear the denominators, but instead of plugging in convenient x values right away, you multiply everybody out and you group like terms, and then you equate the coefficients on both sides. So the number of each kind of like term needs to be the same on both sides because it's an equation. the same number of x's on one side has to be the same as the other side. The constant value on one side has to be the same as the other side. The quadratic values have to be the same as the other side, etc. And so you can actually set up coefficients, equating coefficients to get a system of equations. It's worth mentioning that method 1 can devolve into something like that. So for example, here, if I were to plug in an x value that doesn't eliminate one of the expressions, I would just get something with a and b in it. And I can do that twice and get a system of equations. So you still have that option here. Yeah, sometimes you'd want to mix and match, because sometimes it's not as straightforward as this, where there is a nice x value that's going to kill everybody except the one you want to solve for. And so you can mix and match these methods, but these are the two main approaches that I want you guys to know. And we actually use that on this example. And I left you guys with some other examples to try. And that brings us to today's lecture. Someone's trying to get in here. Okay, so last lecture we learned about partial fractions decomposition. We have some examples to try. So for these, example 1, I just wanted you to find the partial fraction decomposition. You didn't have to do with anything. And in example 2, I actually gave you some integrals to do where the appropriate method would be using partial fraction decomposition. But first, I do want to talk about another method, the cover-up method, which is a shortcut to finding the numerators, these generic constants that I was talking about. And it works in a very particular situation. So here is what the method is about. So let's talk about the cover-up method. So this is a method to find the numerator of non-repeating linear factors. I'll put a little caveat here because there's a little, there's a nuance if you have a repeating linear factor, and I'm going to tell you what that is. But it's a little bit nuanced, so I want to save that for later. So if you had something like, you know, we had 1 over x minus 3 times x minus 2. So these here are linear factors, non-repeating. So they don't have, they're not like raised to a square or a higher power. So cover-up method works here. Similarly, if you have, say, something like x plus 1, x squared plus 1, x plus 3 squared. Okay, just to jog your memory, someone tell me how this would actually break down. Let's see if we can actually use. Someone tell me how this would actually break down using our partial fractions method. What will be the form of the partial fractions? Anyone?
Are we going to break it up into larger fractions? I mean, smaller fractions?
Yeah, like what would it look like? That's what I'm asking. This one, like what would, based on what we covered yesterday, what would this breakdown look like?
A over x plus 1 plus bx plus c over x squared plus 1 plus d over x plus 3 plus e over x plus 3 squared.
Right. So based on what we learned yesterday, that would be the generic breakdown. Now, this here is a linear factor non-repeating. This one is a linear factor, but it is repeating. There is a nuance on this one. And so essentially, the cover-up method would work to find this guy. And it turns out that the cover-up method would work to find the numerator of the highest power of a repeating linear factor. It turns out the cover-up method cannot be used here. Or here. Okay, so that's the first thing you should know is like when it can work, right? So the cover method can work completely on the first example, but for the second example, the cover method can only help us with the A and the E. The other stuff we'd have to do one of the other methods that I mentioned. Okay, so that's the first thing. The method works by how you apply it in practice is like you literally cover something up and you plug in values and then you can find the value that you care about. And so that's why it's called the cover-up method. I've heard another name for it once before. I don't even remember what it is, but I've never heard anyone call it like, I don't know if cover-up method is the official name. I don't think so. It's just something that I've always heard it called because you literally take your finger and you cover something up and then you read off around it. So let's actually see how it works. So let's say, let's go back to our first example. Right. So now I'm going to show you how to use the cover-up method to actually find the A and the B, right? And so this is actually going to be something that is quicker than actually multiplying across, plugging in convenient values, some of the either one of the methods I told you before yesterday, right? So in a very specific case, there is like a shortcut, right? And the cover-up method works in these cases. So here's how you would do it. To find A. Look at the original guy. Like if I was in class in person, I could just like literally show you with my hands what I'm doing, but I can't do that now. So I'm gonna have to describe in words like what I'm doing, and hopefully you'll get it. So you're gonna look at the original guy, right? And you are going to cover up, like literally, like with your finger, like just ignore it, cover up the denominator the factor in A's denominator. So in other words, you have this, right? What's in the denominator of A? The x minus 3. You're literally going to take your finger and cover up the x minus 3. So now what you're visually seeing is 1 over x minus 2. Okay, so that's the cover up method. You cover up with your thumb the factor of that's in the denominator of A, right? And what you're going to do now is you're actually going to plug in the x value that would make that factor 0. In this case, that's x equals 3, right? Plugging in x equals 3 would make the denominator of the A factor 0, right? And so what I'm going to do is I look at the left side, I cover up the x minus 3, and I'm going to actually plug in x equals 3 into the remaining thing that I see. So I'm going to look at now 1 over x minus 2, and I'm going to plug in x equals 3. You'll notice that you get the answer 1. Turns out that's A. That's actually going to be the value, and we've actually seen that. To find B, you would do the same thing, right? To find B, do the same thing. So you'll have this 1 over x minus 3, x minus 2. You're going to cover this up with your finger. And then you're going to take that what's left over, you're going to plug in x equals 2, which is the guy that would make that denominator 0. And so you're going to get 2 minus 3. You'll notice that you get minus 1 as the answer, and that is actually equal to B. So you literally go now and you plug in, oh, the A is 1 and the B is minus 1.
Should there be an x minus 2 in the denominator for the B2?
This one. Right, so that's actually going to be the answer. Let's actually do another example quickly so that you can actually see it. Suppose I told you something like 8 divided by x minus 2 times x minus 4. Okay, we know that this would break down into x minus 2 with an a over it plus b over x minus 4. Now, immediately I can just write this down. And here's what I'm going to do. Cover up the x minus 2. And I'm going to plug in 2. Now, if I cover up the x minus 2 and I plug in 2 into what's left over, what do I get? This is where you guys chime in. What do I get if I plug in x equals 2?
-2.
You would get -2. Like if I take 8 over x minus 4 and I plug in 2 in there. What
Oh,
would
the
I
whole
get?
thing. I thought you were just talking about the bottom, then it would be.
Yeah, no, like it's the whole thing. Like you look at the entire expression once you cover that thing up.
Yeah. So it would be -4.
So it would be -4. It turns out that that's the answer. -4 is going to be the numerator. That's going to be the answer. Now you do the same thing. If I cover up the x minus 4, and then I plug in x equals 4, I would get +4 as the answer. And it turns out that that is going to be what's that should be. So if I look at the, if I look at 8 over 4 minus 2, that's going to give me that. So you can, it's like on the spot, you can actually say what the answer is going to be. So here's another example. 5 divided by, I don't know, x minus 1 times x minus 11. What do I do? Cover this up, plug in x equals 1. I would get 5 divided by -10, that's -1/2. That's the answer. If I cover this up, I would plug in x equals 11. If I plug in x equals 11, I get 5 divided by 10. That gives me +1/2. Turns out that's the answer here. All right, so I can literally just see what the answer is by just covering one factor up, plugging in what would make that factor 0, and that's going to be the coefficient. It doesn't have to be like negatives. I mean, I could go like an x minus 2 times an x plus 2. Of course, that's going to be an x minus 2 here, x plus 2 here. Cover this up, plug in x equals 2. You would actually get 1. That's the numerator. If I cover this up, plug in x equals -2. You get -1. That's this numerator. Done. And you can actually do this for non-repeating linear factors, and it doesn't matter how much. So I can have something like, I don't know, 16 over x minus 1 times x plus 3 times x plus 4. So this would actually break down to x minus 1, x plus 3, x plus 4. What goes on top of the x minus 1? Well, I cover up x minus 1 on the left, and I would plug in x equals 1. So that's going to be 16 divided by 4 times 5. What's going to be on top of the x plus 3? Well, if I cover up the x plus 3 on the left and I plug in x equals -3, I would get 16 divided by -4 and 1. What's going to be on top of the x plus 4? Well, if I go to the left and I cover up the x plus 4, I would plug in x equals -4. I would end up with 16 divided by -5 times -1. And that's actually going to be all the coefficients. So this is going to be 4/5. This one is going to be -4. And this is going to be, well, plus 16/5 over the x plus 4. And that's the partial fraction decomp. So cover-up method is actually really nice. In the case where you have a repeated linear factor, so let's say, I don't know, 6 over x plus 1 times x minus 2 squared. Right? Cover up is going to work here and here. So it's not going to work here. I can put my generic B there. But essentially, for the other two, if I look on the left side, I cover up with my finger the x plus 1 and plug in x equals -1, right? I'm going to get 6 divided by -3 squared. For the x minus 2 factor, if I cover up the x minus 2 squared and plug in x equals 2, I would get 6 divided by 3. It turns out that those are going to be the numbers. So then I would end up with, that's 9. So this is going to be 2/3 plus some b over x minus 2 plus 2 over x minus 2 squared. Okay. So I've done 2/3 of the work, and I've done it pretty easily, pretty quickly. It's just a matter of, arithmetic. So you cover up one thing and you plug in those things. Now, how do you find the b? Well, you just bite the bullet and do one of the two methods that I showed you yesterday. So you would multiply through by the denominator on the left. So this would give you 2/3 x minus 2 squared plus b times x plus 1 x minus 2 plus 2 times x plus 1. But at this point, notice that if I plug in an x value, I would just have b being the only unknown. So let me just plug in something random and easy, say x equals 0. This equation needs to hold for every x, so it's going to hold for x equals 0. So this means 6 is 2 times 2/3 times minus 2 squared plus b times minus 2 plus 2. So then I have 6 is equal to 8/3 minus 2b plus 2. And now I just have an equation with b. I can solve for that b. So, I mean, generally, I would have had to do this for all 3 of those guys. But in this case, I can only do that for one of those guys, because these first 2, I can pretty much know what the answer is. Like, I don't even have to write out steps. I can know it in my head because I use the cover-up method. So cover-up method gets 2/3 of the work out of the way very quickly. And then I just do the calculations for the last one. So here you would have, say, 2b would be equal to 8/3 plus 2 minus 6. Well, 4 is going to be like 12 over 3. So that's going to be minus 4/3. And so your b is going to be minus 2/3. And so I can go back in the original, the 6 over x plus 1 times x minus 2 all squared. That's going to be, what were these guys? 2/3 over x plus 1 minus 2/3 over x minus 2 plus it was 2 over x minus 2 all squared. So I can actually have the partial fractions there. So it turns out you do the math, you combine all the three fractions on the right side, you will actually get the fraction on the left side. It's also worth mentioning that in terms of integration, integrating the right side is very easy. They're all basic rules. The first two is just going to be ln. The last one is going to be power rule. So they're very easy to integrate. Whereas the guy on the left, not so easy to integrate. At least not just like off the top of your head. Like you can integrate the right side off the top of your head. It's going to be, 2/3 ln absolute value x plus 1 minus 2/3 ln absolute value x minus 2 minus 2 times x minus 2 to the minus 1 power plus c. That's going to be the answer. Like you can read it off on the right side. You can't really do that on the left side. Like if all I knew was this left side, like I'm not going to integrate that in my head. No way. But the right side isn't so bad, right? So this shows you the power of partial fractions, and the cover-up method is actually a shortcut that we can do. So that's pretty cool, I think. And, first time I was learning Cal 2, no one told me about the cover-up method. I learned this afterwards. So yeah, I just want my kids to be better, have it better off than I did, so telling you guys the tricks no one ever told me. So hopefully you guys make good use of it. So that's essentially the cover-up method. It works by literally covering up parts of your expression, plugging in the correct x value, and then you can work on the other thing. It doesn't work for nonlinear things. So like I can't use the cover-up method to figure out what would be like, where do we have it? We did an example. Yeah, like this. Like the denominator being x squared plus 1, I can't really use the cover-up method there. Generally speaking, the cover-up method it's an application of a theorem in complex analysis called the residue theorem. And it turns out once you go higher than a linear power, it's not as straightforward to actually figure things out. You'd have to like multiply by something and take a derivative, and there a lot of other things come into play once you go quadratic and higher. But with linear and lower, the theorem, the residue theorem, essentially means you have to take a 0th derivative, which means you don't really have to take any derivatives at all, and you can just plug in a convenient number. So it's really nice. There is a nice algebraic way, I guess, to see why this actually makes sense or why this would work. So the thing is, why does this work? So the thing is, so let's say we started here, x minus 3 times x minus 2, and we know that becomes, let me just show you why it works. So covering up what the mathematical operation that you're doing that you're just not writing down when you cover up is actually a multiplication on both sides by that factor in the denominator. So notice that if I multiply by x minus 3, then the equation would become 1 over x minus 2 equals a plus b over x minus 2 times x minus 3. Notice that if I multiply the equation by x minus 3, that's what I would get. Now, if I actually plug in x equals 3, Notice that this part here, that would be 3. This part here is just going to go to 0. So really, you've isolated the A by doing this, right? So, and the what's on the left side, you'll notice that it's what you would get if you looked at the original left and just covered up the x minus 3, just ignore the x minus 3 part. Really, you didn't really ignore it, but you actually multiplied by it. And that factor is going to be in everybody except the A. And so when you plug in x equals 3, it kills everybody except the A. And you can actually do this for the other one as well, right? Similarly, multiply by x minus 2. That would give you 1 over x minus 3 on the left. You'd have A over x minus 3 times x minus 2 plus b. And then if you plug in x equals 2, you get 1 over 2 minus 3 equals 0 plus b, right? You'll end up finding the b that way. In the event that you have like a repeated linear factor, so let's say I had 1 over x plus 1 times x plus 2 squared. We know that this would break down into that. So if I multiply by x plus 1, this would give me 1 over x plus 2 squared equals a plus b over x plus 2 times x plus 1 plus c over x plus 2 squared times x plus 1. And then these guys would disappear if I plug in x equals minus 1, and I can only solve for the a. Now I can solve for the c by multiplying by the x plus 2 all squared. Then I would have 1 over x plus 1. I would have a over x plus 1 times x plus 2 squared plus b times x plus 2 plus c. And notice that these two guys would go to 0 if I plug in my x equals minus 2, and I would be left with the c. A similar thing can't work with the b, because if I only multiply by one factor of x plus 2, the c would still have x plus 2 in its denominator. And of course, I can't plug in anything that makes that 0. So that's why it's not going to work for the b, because I have to multiply by the highest factor possible, or else I'll still have denominators that are an issue. So a nice little non-complex analysis way to show you why this actually works. But that is essentially, in practice, how it would happen, right? So you have a non-repeating linear factor, or the highest the highest power of a repeated linear factor. You can just cover that factor up on the left, plug in what would make that factor 0. That will be the arbitrary coefficient. And that works in this very specific case, right? It only works for linear factors. So if you have a quadratic, you just have to do it one of the methods that I taught you last time. And so this is just, it's something additional. So it's actually will save you time if you learn it, but you could actually do everything with what I taught you yesterday. So this will just make your life a little bit easier in some very specific circumstances, which happen to be pretty common in a Calc 2 class. So that sort of brings us finally to these examples. I ask you guys to try. So we'll try it. And in today's lecture, whenever it's possible to do like a cover-up method, I'm going to do it. Even though yesterday when you tried it, you probably didn't have that at your disposal. That's understandable, but at least you'll be able to appreciate like how much time you would have saved if you knew the cover-up method. And hopefully that's going to incentivize you to try to use it in the future. So you don't have to. I mean, I'm just trying to make your lives easier. I have another message here. Okay, I hear you, Mom. Yeah, so what do we have here? So we maybe someone can tell me what they did with this one. Just walk me through what you tried. And if anyone tried and got stuck, that's good too. So we can actually deal with whatever issues there are. First of all, can partial fractions work on this one as written? Like, what are the things we have to check?
Like, is it proper or not?
Is it proper? So the first thing is it proper? It's yes, it's proper, right?
The base, the degree of the base is bigger than the degree of the numerator.
Exactly. And it has to be strictly bigger, right? So that's important. So if the degree were the same, it's not proper still, according to our definition. It has to be strictly bigger. So the degree of the base is 3. The degree of the numerator is 2. 3 is strictly bigger than 2. Therefore, it's proper. Right? Because the degree of the numerator equals 2, which is strictly less than the degree of the denominator, which is 3. So it is proper. And so that's the first thing. The second thing is the denominator needs to be factorable. Right. So that requires some insight from, say, pre-calculus, where you should be able to like see whether that's factorable or not. Is it? So this is 5x squared plus 20x plus 6. What would the denominator factor as? I mean, let's not write it out here. Let's write it out here. So x cubed plus 2x squared plus x. If you had to factor that fully, what would that look like?
X times x plus 1 squared.
All right, x times x plus 1 squared. You'd factor out the x first. You'd get that. Then, you do that, the whole thing. Two numbers, when you multiply, you get +1. Add them, you get +2. Plus 1 and plus 1 work. So you get x times x plus 1 all squared. So yes, it's also factorable. So this gives us the two things that we need for partial fractions to actually work. Now, once partial fractions, I know partial fractions is going to work. We have a method to do that. So that's 5x squared plus 20x plus 6. And the denominator is going to be x times x plus 1 squared. So what is that going to break down into? Like the generic factors. Or the partial fraction decomp look like? Come on, don't be shy. Want to know what you guys know. Because there are some problems in the homework, I believe, where you're literally only asked to do that. They don't even ask you to find the A, B, and B's. And I might ask a problem like that on the test where there's just like one problem or a part or a problem where I just want the breakdown. Like even if you don't solve for the numbers correctly, you can still like get that problem fully correct. So I want to make sure you know how to do at least that. And then solving for the numbers is a whole other thing.
I don't know how to do this with like the polynomial on top. I think that's like where my issue is. And how do we turn that into a fraction?
Okay. Do you know about the denominators then? What would the denominators be?
I think that the denominators. One second.
Would it be x plus 1 and x plus 1 squared?
Okay, so that's half the problem done. What's the, so now let's get to her question of what is the numerators look like for the x? What's on top of the x?
A,
It's just a. Why is it a? How do you know it's just a?
blind guess.
Blind guess, okay. All right. Does anyone know why it's just a? Like, what is the rule that we're following that we just write a?
The degree of the numerator must be exactly one less than the degree of the denominator.
Right. So the factor here has power 1. It's a first degree polynomial, which means that the numerator has to be 0 degree polynomial. A 0 degree polynomial is a constant. Same thing here. And actually, same thing here. Now, this last one, if we weren't paying attention yesterday, is probably going to be a little bit confusing. But I actually showed you why this has to be the case. But to avoid confusion, what you should be focusing on is the base factor. The guy that's inside the parentheses is what's important. Right? So if it were something like, right? What you're focusing on is the base factors. Right? The rule doesn't apply to whether it's repeated or not, right? Repeated means you have to list things out this way, but when you're looking at the rule to apply to the numerator, you look at the base factor. And in the first case, like we said, because it's a first degree polynomial in the denominator, it must be a 0 degree polynomial in the numerator. For the second one, because there is a second degree polynomial in the denominator, there must be a first degree polynomial in the numerator. So that's ax to the first power plus b. And the same thing, not a, we already used a. We're on b and c. And similarly, you're going to have dx plus e. ETW. Okay, so that is the rule. So you break up into smaller fractions based on the denominator, the factors in the denominator of the big fraction. And then on top, you put generic polynomials that are exactly 1 degree less than the base factors in the original. That's the rule. You do those two things and you're done. Okay, so now question is, how do we go about finding the A, B, and C? Well, I can use the cover-up method for the A. Right? So the cover-up method basically means I'm going to take this guy where I ignore the denominator of the A and then plug in x equals 0, which would make the denominator of A equals 0. So that's just going to be 6. That's your A. For C, I look at this guy. I cover up the denominator of C, and I'm going to plug in what would make that 0, which in this case is x equals -1. So that would be 5 minus 20 plus 6 over -1. So that's what, 9? Because 5 plus 6 is 11. 11 minus 20 is 9, and minus 9. And then you divide by a -1, so that makes it +9. So that's your A and C right there. To find the B, we can do that thing where we multiply both sides. By the denominator on the left. So I'm going to have 5x squared plus 20x plus 6. If I multiply both sides by x times x plus 1 all squared, in the A term, the x is going to cancel. In the B term, the x is going to stay and 1 factor of x plus 1 cancels. In the C term, the x plus 1 all squared cancels, and I have this. But I actually know what the A and the C are. These are 6 and 9. So I can actually even write these out.
Oh,
Yeah, Joshua, you have a comment?
no, I'm good.
Okay. So now we have that equation, and we can just now plug some random number in that's going to help us solve for the B. So essentially here, you can plug in anything, just don't make it something that would actually kill the B, right? So I'm not going to plug in x equals 0 because that's going to kill the B term. I'm also not going to plug in x equals -1 because again, that's going to kill the B term. But I can plug in literally anything else. So I wouldn't plug in like 5,673 because that just makes my life harder than it has to be. I'm going to plug in something small that I can actually compute relatively easy. So I'm going to plug in, say, x equals 1. Then the left side is going to be 5 plus 20 plus 6. This is going to be 6 times 4. This is going to be 2b. This is going to be 9. So on this side, I have 31 equals, well, 24 plus 9. Right? So that's going to be 33 plus 2b. And then move the 33 to the other side. So your b is going to be -1. And so that means my original guy, 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x right? That actually breaks down into a over x, but a is 6. B over x plus 1, but my b is -1. Plus c over x plus 1 all squared, but the c is 9. And so that's my partial fraction decomposition. And again, if I had to integrate the guy on the left, like good luck, but the guy on the right, trivial, right? The integral of that be 6 ln absolute value of x minus ln of absolute value of x plus 1 plus, well, minus 9 times x plus 1 to the -1. So yeah, partial fractions, we could use that to actually integrate the left side pretty easily. Okay, so lots of things happening here. I also use the cover-up method. So that's what happened for these two. But you could actually do something similar to here where you plug in convenient x values into this equation here, which is what we spoke about yesterday. But yeah, before we move on, any questions on this? Any part of the process? So in step 1, do we understand how we got the denominators, how we got the numerators? And do we understand how we solve for these guys? Any questions? Comments, concerns? Okay, so we are going to continue when we return from the break. So we'll stop there for now. Take a quick 5-minute break, regroup, make sure you understand what happened here, and we will pick up with the other examples later on. Okay, all right. See you guys in a little bit. All right, we are back. So one thing, because I do want you guys, you know, to actually look at some stuff. I think I will jump into the integration and maybe leave these two for you guys to try, and then you can tell me what you think the answer is. Gonna do one more example because I want to get to the integration. So we're learning a lot of stuff on this one. I don't want you guys to want you guys to actually sit down, absorb it, and practice some a little bit. So try these on your own. You can know if you're right. You can check your answer by combining your partial fractions on Wolfram. Right, so that was one of the resources we left in the syllabus. So for example, let's say I actually wanted to check this, right? So I did this, you know, and I'm just like some new student. I don't know, is that right? Did I do everything correctly? Like you can't actually check it. So maybe I should show you how to check that. So here we are in Wolfram Alpha, and you can actually check your answers here. So we got, for the last one, let's say we wanted to combine 6 over x minus 1 over x plus 1 plus 9 divided by x plus 1 squared. Yeah. There's our answer. That's actually our guide. So notice that by combining these guys, I can actually get back my original. So I know those are the right numbers. A was 6, B was minus 1, C was plus 9. So that is just something you should know. You cannot always check. So these guys, it's just you breaking things down. It should be easy to check whether you're doing it right. So that's the first thing. So I'll leave these two guys to you to try your stuff on to make sure that you understand it, and you guys can ask me questions. And then we'll just do one more, and we'll do a bunch more examples when we're getting to integration. So we're still going to have a lot of partial fractions to get through. But I want some extra practice for you. I did get a question in the chat about how I got the A and the C. So in this situation, I got that from the cover-up method, which I actually taught you guys earlier today. So I know it's probably hasn't sunk in yet, but this is essentially the method, right? Where I covered up what was in the denominator and I plug in. So the question was, how did I know what to plug in to find the A? Well, I use the cover-up method. So that says, if you look at the partial fraction, the denominator of A is x, which means I look at the original thing, which is this guy. I cover up the x, and then I plug in, and that would give you this guy. And then I plug in whatever makes x 0, which in this case is x equals 0. And that will give you the value for A. Now, when it came to finding the value for C, it's the same idea. I go to the original, I cover up the denominator of C. I would end up with this expression by covering it up. And how do I know what to plug in? I plug in whatever x value makes that denominator 0. So the denominator is x plus 1. So x equals minus 1 would make that 0. So I plug in minus 1. And that gives me the 9. So that's how the cover-up method works. You go to the original, you cover up the denominator, you plug in what would have made that denominator 0. That's going to give you the coefficient. This works for non-repeating linear factors. So like this guy comes from a non-repeating linear factor, or it comes from the highest power of a linear repeating factor. So this guy. So that method only applies to these two. You cannot use that method for the B. So just so you know, right? So I did use the cover-up method though. And as you can see, like this, I mean, I wrote it out for the benefit so you can see what I'm thinking, but generally, like I wouldn't even have to write this out. Like I could just see the answer. Whereas not doing that and trying to do something more traditional, like the methods I taught you yesterday, it takes some time to actually work through it. It's essentially arithmetic and algebra, but it takes a while to actually get through it sometimes. So if you can avoid that, you can do it. And the cover-up method allows us to avoid that in certain situations. So. Something else. My video had disappeared on my screen here, so I'm wondering, is it seeing me? Okay, yeah. All right, so that's how we got those guys. Let's talk about this one. So can we do partial fractions on this?
I don't think so, because both of the same degree.
Right, so not proper. So what do? You have to transform it, right? A bunch of methods. Let me show the algebraic way. Remember, the trick here is just get the denominator and the numerator. So if I have x squared minus 1 plus 1, that allows me to get this this x squared minus 1, which is in the denominator, gets me in the numerator. And then I just split that fraction across both of these guys. So this actually splits into that. Right? And so now I can do partial fractions on this guy. How do I know it works on that? Because the denominator factors, right? So that's the difference of squares. So maybe I should actually write this. Right, so originally I couldn't actually do the partial fractions method on the original one, but by doing this algebraic manipulation, I can get it to work on this. To me, that's the faster way, but I can show you the long division way if that makes it easier for you. So the guy that it's x squared minus 1 over here, divide into x squared. So you take the first guy into the first guy, x squared divided into x squared goes 1, take that 1, multiply everybody there. Subtract that line, that cancels that, and minus a minus 1 gives me plus 1. That's my remainder. So this means I get 1 plus 1 over x squared minus 1, where maybe I'll make that a different color. So the 1 up here, just made that green. That would be this one. And the 1 right here, just made that red. That would be the guy that I put on top here. And as you can see, that's the same thing that we got before. So that would be the long division. The algebraic manipulation, just subtracting 1 and adding 1, then splitting the fraction gets you there pretty nicely. So now, I want to do partial fractions on this guy. So now. So now notice that both the x minus 1 and the x plus 1 are non-repeating linear factors, which means my cover-up method could work. So I look at this and cover up the x minus 1, plug in x equals 1, right? Because that would make the x minus 1 0. And then cat is speaking most time. Then you would get a half as the answer. And so that's what goes on top here. Then I would cover up the x plus 1, plug in x equals minus 1, because that's what would make that 0. The answer would be minus a half. So that's it. And so the original x squared over x squared minus 1, this breaks down into 1 plus a half over x plus x minus 1 minus a half over x plus 1. And that's the partial fraction decomp. Any questions on that one? Can I see what's going on? Any final questions before we move on to the okay, I got him away. He was scratching behind me. I don't know if you guys could hear that, but it was distracting me. Okay, so let's move on. So actually try your hand at these two. We're actually going to move on because you know, kind of feel like we're back in algebra class. I want to get to some calculus. Let's do that now. So our focus really should be integration, but let's get back to it. So let's actually do these integrals now. Okay, so let's say you show up on a quiz or a test and you see this guy. Like, what are you gonna do? Yeah, so you're like, basic rule? No. Can I simplify this? Substitution, like obviously substituting like the denominator is not going to help you. The numerator is not agreeing with you. Man, like, I wouldn't be brave enough to like complete the square and even try a trig sub on something like this. That's just does not seem like a good idea at all. Integration by parts, forget it. But it is a rational function. And it turns out that the denominator does factor. So that kind of gives me the idea that partial fractions might be something that's doable. However, you'll notice that it's not in the right form for a partial fraction. So I would probably need to fix that. So again, you go through the whole basic rule. Simplify, substitution. Right? All that stuff, right? None of that's gonna work here. Okay, so now that we've decided that, and we realize that these aren't really options, now we can actually get into like how we'd actually attack this. So for whatever reason, you're gonna think partial fractions here because by parts or trig sub does not look like a good idea either way. So of course it's not proper, so that's the first thing you're going to want to do. So you have this 4x squared minus 3x plus 2 over this 4x squared minus 4x minus 3. So how do we actually get this to be proper? Can use the algebraic manipulation trick. So 4x squared, I want to get the denominator in the top, so I'm going to add a minus 4x minus 3 and then subtract them again. So that leaves me with 4x squared minus 4x minus 3. What's left over is I have a 4x minus a 3x, so that's plus x. And I have a 3 plus a 2 plus 5. Now, of course, I can split this fraction across these two. And so I'm going to end up with 1 plus x plus 5 over that 4x squared minus 4x minus 3. Okay, which is now a proper fraction. In fact, this I can realize is just x plus 5 over, what would this actually factor into? And let's try a 2x and a 2x. The only way to get that is a 3 and a 1. If I do 2x, 6x, can I make that a 4? Yes, if this is a minus 6 and a plus 2, that works. So that's the factors. So if I were doing a partial fraction, there'd be a 2x minus 3 here, the 2x plus 1 here. And I want to make sure that that's going to work out. Now, these are non-repeating linear factors, so I don't need to go to the side and do that whole partial fraction thing. I can just do the cover up method. So if I cover up the first one, so I take x plus 5 over 2x plus 1, and I plug in x equals 3/2, because that would make that denominator equal 0. Then I would get 3/2 plus 5 all over 3 plus 1. In other words, that's 3/2 plus 5 all over 4. Multiply top and bottom by 2. I would get 13 over 8. Looks like. So I can actually plug that in here. And then if I do the other one, take the x plus 5, cover up the 2x plus 1 and just leave the 2x minus 3. And then I plug in x equals minus 1/2, because that would be what I need to make 2x plus 1 equal to 0. Then that's going to be minus 1 over 2 plus 5 over minus 1 minus 3. So that's going to be minus 1/2 plus 5 all over minus 4. Multiply top and bottom by 2. I would get minus 1 plus 10. So that's 9 over minus 9 over 8. And that is what goes here. So, if I call this I is actually equal to the integral of 1 plus 13 over 8 times 2x minus 3 minus 9 over 8 times 2x plus 1. Integrating the 1, you get x. Integrating this one, you get 13 over 8 divided by 2 ln of 2x minus 3. And here you get 9 over 16 ln of 2x plus 1. Okay. So, questions? Did I lose anyone anywhere? And this is essentially me doing an integration via partial fraction decomposition. It's an integral of monster fraction, and I broke it into smaller fractions, where each of those were easier to integrate. If there are no questions, we'll move forward. Now, this one might seem a little bit weird because of that radical x. And you might have noticed this, and I'll definitely make this explicit at some point, but the whole partial fractions thing, it needs like polynomials to work, right? So this radical x doesn't really work, right? It's not technically a rational function because you don't have x, all the x's to non-negative integer powers. Any ideas on how to deal with that?
Multiply by x over x. Oh, sorry, rad x over rad x.
I mean, okay, so you would get x over x rad x minus 4 rad x. Does that help? Is that better? In some sense, it's better that it might actually help you see what you want to do. I mean, if you think of it like this, does that make it a little bit clearer on where you kind of want to go? I'll tell you what writing like that reminds me of. Take the derivative of a radical x. The answer has a radical x in the denominator. Notice over here, we have a radical x in the numerator, but you can actually conceive of it as something with a radical x in the denominator. This kind of tells me about like a differential kind of operation thingy going on, which hopefully, and again, by going through this thing in your head about how to approach integrals, a substitution is probably how you want to start this. You see this and you're like, that looks ugly. But at the same time, I don't really have a nice method to work on this. You're always going to think, can a substitution work? That's always going to be something in your mind. And you're like, well, if I wanted to substitute something, I definitely want to get rid of that radical x. I also can recognize that x is really, I can think of that as radical x to the minus squared if I wanted to. You know, that would have to be true. Because for radical x to work, your x has to be greater than or equal to 0. And so x in this case would be that. And in other words, if I just replace the rad x with a single variable, like a non-radicalized variable, that kind of makes it look more like a polynomial. So probably starting this off with a substitution would be nice. So I would go in and take our integral, which I call this I, and I can now start swapping things out. So the radical x, I'm looking at this version here. So everywhere I see radical x, I can put u. And then where I see the dx, that's just 2u du. So that's my integral now. So this is just 2 times the integral of u squared over u squared minus 4. Now substitution brings me to a point where it's a little bit more palatable, but it doesn't really get me to an answer right away. But at this point, it starts to make me think in a certain way, and it starts to make me think, oh, this is just a rational function. Technically, you could do a trig sub here, but probably, as I kind of mentioned, you probably want to avoid trig sub if you can. It's kind of the bastard child of the integration techniques. You don't want to get into a trig sub unless you like have to get into a trig sub, right? And now with partial fractions, you have another option because the denominator of this guy factors nicely. It's just a difference of squares. However, it's not proper, but that's not really a big deal because I can just go like -4 + 4 and make it proper. Right, so not being proper wasn't a big deal. In fact, this is this guy, not x, u. And in fact, I know with partial fractions, that's going to be this. Now, to figure out what's in the numerators, non-repeating linear factors, I can actually get these easy with the cover-up method. So I look at this one, cover up the u equals -2, plug in u equals 2. I would get 4 divided by 4, which is just 1. And so that's the answer there. If I cover up the u plus 2 and plug in u equals -2, which is what would make u plus 2 equals 0, I would get 4 divided by -4, which is -1, and that goes there. So ultimately now this integral, radical x over x minus 4, is actually equivalent to this integral. And this one is actually not so bad. That would be u plus ln of u, u minus 2 minus ln of u plus 2. But if, our u was actually, now we do our back substitution, u was radical x. And that's our answer there. So for this integral, we needed both substitution and partial fraction decomp. So I did a substitution because it would be the third thing I would think of, and I would definitely want to kind of make this look nicer. So I'd want to get rid of that radical x. And when you see something like this, you see like a radical x, and you have a bunch of other x's that aren't radicalized. What you might want to do is a substitution, because you can always write those other x's as like some power of the radical x, right? So you can do that, and then you end up in this situation where you have like a u squared over u squared minus 4. Technically, you could do a trig sub, u equals 2 secant theta. You can go through all that, and you would eventually get to an answer, but it would be longer than this answer, for sure. At this point, could do a trig sub. U equals 2 secant theta. But why? Why would you do that to yourself? It's harder. We have more sophisticated ways of dealing with this now. I mean, if you find yourself in a test and you can't think about the partial fractions, I guess you can do it the trig sub way and you'd get the answer. You'd work a little harder, spend a little more time, but so that's another trap that students, it doesn't happen often, but it happens enough for me to say it. Sometimes students want a nice answer. They're like, yeah, I want the answer that lets me look cool. And they try to find a clever way to get to an, like, if you can't think of a clever way, just brute force it, just do it the ugly way and don't worry about it. Like, you don't actually get points for looking pretty at this point. So yeah, a trig sub would be a much uglier way to finish up this problem, but if that's what you saw, you could actually do that. But partial fractions is actually much nicer and much easier, I think. Especially once you actually get the cover-up method and you can like do that on the spot instead of like going to the side and setting up these systems of equations and coming back, like it's clearly the winner. All right, I've been talking for a while. Maybe someone can tell me what they would try for this one. Any ideas?
Maybe substitute e to the power of x minus 1 for u.
E to the power of x minus 1. Why do you want
I
to
mean, e to the power of x.
Yeah, the -1 is going to cause issues on this part right here. Yeah, so That's probably the first thing I would think, like, that would actually get rid of the e to the x in the numerator, so that would be nice. So yeah, like eventually you go through the hierarchy, obviously it's not a basic rule, simplify it, come on. So a substitution, can that work? U equals e to the x might be a nice substitution to work. And so your du will be e to the x dx. And then you go through and you plug this in. All this I. And so your e to the x dx is just du. Let me put that off to the side. And then now, because your e to the x is u, this part here is u squared. This part here is just u minus 1. Now that guy is something where, yeah, at this point you wouldn't think a trig sub, because that part would be very annoying to deal with a trig sub. The u squared plus 1 is nice for a trig sub, u equals tangent. But the u minus 1 kind of messes that up. And if this were like a u squared minus 1, even worse, because then you're in a situation where for one trig sub, you'd need a tangent, for the other one, you need a secant. You can't do both, obviously. But here, yeah, so trig sub isn't even on the table anymore. But at this point, we can do a partial fraction decomp. Now this is going to be those are the factors, because u squared plus 1 cannot factor further. What are the numerators here? What is the numerator of this guy?
Be AU plus B.
Mm-hmm. And this guy would just be C. Right? So that's the integral we want. So now let's actually figure out what that is. So here, let's go do our partial fractions. I mean, I probably. Partial fraction. I probably don't want to put that in a different coloring, because I would expect you to show this. So originally our guy was 1 over u squared plus 1 times u minus 1. And we broke that down to AU plus B over u squared plus 1 plus C over u minus 1. Now, one of these guys we can actually find relatively easy. Just using the cover-up method, we can find C. So to find C, I'm going to cover up the u minus 1 and then plug in u equals 1, right? So I take 1 over u squared plus 1, plug in u equals 1. That would give me a half. And so that tells me my C is a half. All right, so now all I need to do is to find the A and the B. And that's not as straightforward, because the cover-up method won't work there, because the denominator is not a linear factor. So cover-up will not work there. So this means I'm going to use one of the two methods that we did yesterday, which for either one, we are going to have to clear the denominators. So here I multiply through . So the u minus 1 would cancel off the c term. You'd be left over with a factor u squared plus 1. For the au plus b term, the u squared plus 1 would cancel from the denominator, and we'd be left with a u minus 1 factor. And so we have this equation. And so at this point, there are a couple ways to proceed. You can plug in two different values of u and get two separate equations for u and v. The other thing you can do is you can multiply out group-like terms, and then you can find the values of u and v that way. So we have a couple options here. So let's say I went with multiplying out, because that's kind of the way I had you do it yesterday. So this would be au squared minus au plus bu minus b plus 1/2 u squared plus 1/2. So I'm going to group the u squares. So that's a plus 1/2 u squared plus group the u's. I have minus a plus b times u. Group the constants. I have minus b plus 1/2 for the constant. And so this guy must be 0 because there's 0 u squares on the left. Right over here, I have 0 u squared plus 0 u plus 1. This guy must also be 0. And this guy must be equal to 1. So I get this system of equations. A plus 1/2 equals 0. Of course, that means your a is minus 1/2. Minus a plus b must be 0. So this would also mean that b equals minus 1/2. They're both like minus 1/2. And if minus b plus 1/2 equals 0, again, you get just a verification that your b is, it's 1. So it's also minus 1/2. So both your a and b are minus 1/2. And so I would go back here. What do we have? The integral of au plus b over u squared plus 1. And our c is positive 1/2 over u minus 1. The halves are kind of annoying. Let's factor those out, maybe factor out a minus 1/2. And I would have u plus 1 over u squared plus 1 minus 1 over u minus 1. So that looks a lot nicer. How would we actually do that? So the last integral, this guy is no big deal. That's just your ln, right? This guy's the challenge. How would we do that?
I don't know if it's the most efficient way, but it does kind of scream trig sub.
Okay. Right, not the most efficient way. Think about a different way. Think about trig sub like pressing the nuclear launch button, right? So if you're like, man, we should launch these nukes, there should be a guy in the room that goes, wait, are we sure we want to do this? Right, you always second guess yourself. Any other option? Anything else you see that might work? I mean, it's nice to notice that there's a u squared in the denominator and a u in the numerator. Does that suggest something? Like, turn the clock back to like Calc 1. You see something like this guy, what would you have done? Like, technically a trig sub can work, but it's not the best way to approach it.
Can you just do another, not a u sub, but another substitution? New
Right, to
variable.
do a substitution, right? So for this, you would like substitute what?
X squared plus 1.
Right, so your du would have been 2x dx. And so this whole integral would just be 1/2 1 over u du, right? And so it's 1/2 ln of u. So it's 1/2 ln of x squared plus 1. Right, that would be what you would have done for this guy. Okay, so now, knowing that, we're here. Did that help at all? Ideas now? Could we do a substitution on this one?
You can split it up into two integrals. The second will just be a natural log. And the first, the substitution will cancel out the u's.
Right, so here, can split this up. This is u over u squared plus 1, plus 1 over u squared plus 1, minus 1 over u minus 1. Right, in fact, for clarity, let's just actually make these three separate ones. So minus 1/2. Split this up into u over u squared plus 1 du. Okay, so now for the first one, it's actually exactly the same as the example I gave you to the side. It's a substitution, right? So you do like a t sub maybe, t equals u squared plus 1. And the answer would end up being 1/2 ln of u squared plus 1, right? Via the same thing I said earlier. What about the second one? What's this? What's the integral of 1 over u squared plus 1?
Ken,
Come again?
10.
Arctan, right? That's the generic formula, right? So this is just arctan. Maybe parentheses here, but arctan u. And for this one, again, technically it's a substitution, but your du just equals dx. So there's just a coefficient of 1 in the front. So this here is a basic rule. And this here, I guess you can say a t equals u minus 1 substitution. But it's a straightforward substitution. You can pretty much do it without substitution in your head. Because the derivative is just 1. The derivative of the thing you're substituting would just be 1. So dt equals du, you just ignore everything and you put it back. We're not actually done because we did start this whole thing off with a u equals e to the x. Let's not forget. So we're going to have to do our back substitution here. This minus 1/4 ln of e to the 2x plus 1 minus 1/2 arctan e to the x plus 1/2 ln of e to the x minus 1. Let's see. And that's that one. So that was actually a pretty long one. I don't know. Can actually even see all that here. But you start off doing a substitution to make it look nicer. You realize you get something that's a prime candidate for partial fractions. You break it up according to the rules of partial fractions. Cover-up method helps you find the C pretty easily. For the A and B, I did method 2 from yesterday. Multiply out, combine common terms, set up systems of equations based on the coefficients I saw for A and B. Go back and plug these guys in. I factored out a -1/2, again, just to make it look nicer. And for the first integral, splitting it up into 2 other integrals makes sense because one of them is a basic formula, the other one is an easy substitution. This one is also an easy substitution, and I get that. And then I back substitute for the e to the x to get that final answer. And that's where we are with that one. Okay, this one we're going to take another 5-minute break. Try the others. There are some left over here, so there's like that cosine. I mean, I think you guys have the notes, but we'll finish these when we get back. Yeah, so I'll see you guys in a little bit, 5 minutes. Drink some water, stretch your legs, and we'll be back soon. All right, we are starting again. Okay, so let's actually get through these other guys. So again, so we're gonna, I taught you everything about partial fractions and all of that, and hopefully it's trying to get to sink in. So for these few remaining ones, I kind of want to just discuss through my head through first principle, like what you would think about when you see this. So we're just pretending, let's forget we're in the partial fraction section, all that, just seeing this is some random integral that I encounter in the wild, in life, on a quiz, on a test somewhere, but I need to solve it, right? Like, what are the things you should think about? So again, you always start to think, well, does this random integral look like a basic rule? And basic rule just means it looks like one of the rules in the chart, right? So where did I put that chart? Was that lecture 2? I think that was lecture 2. So there's a general chart here of all these rules that we consider them to be basic rules. And I would add to that chart, I mean, I wrote it down here, you should know what the basic rule for the integral of ln is. And I would probably also add to that chart the integral for secant cubed. We also added, I believe, the integral for secant cubed. It's 1/2 secant x tan x plus ln absolute value secant x plus tan x. Right? So these are your basic rules, right? Always in the back of your mind, you're always trying to see, does the integral I'm looking at look like one of these guys? Does it look like the left side of one of these equations? The moment you get to that point where it looks like the left side of one of these equations, the answer will look like the right side of one of these equations. So you just write that down, okay? So that's always the first thing you're thinking. Is it a basic rule? Can I do that? The next thing you're going to think about, can I simplify this? Like, if that's not true, can I simplify it so that the pieces look like one of these basic rules? That would be the second thing you want to think. And if that doesn't work, then you might think, can a substitution work? But again, the whole point of substitution is to rewrite things so that it looks like one of these basic rules. Everything comes back to these basic formulas. Everything you do is to kind of break whatever you're seeing down to look like the left side of one of these equations. Once you get to that point, you'll be able to know what the answer is. So this is always in the back of your mind. It's always one of the things you're thinking about all the time. So I see this random integral. My first thought is that a basic rule? Is there something in that table that looks like this on the left side? And the answer is obviously going to be no. Then you think, well, what if I simplify it? Can I get it to look like a basic rule? Well, there's no obvious way to simplify this one. So the third thing you think is, could a substitution work, right? Can I say, like, replace an expression in this thing with a single variable that's going to make life easier, make it look nicer, make it look like a basic rule? That would be the next thing that you would think about. So here, you might think, okay, if I had to do a substitution, what would my substitution be? And hopefully through Calc 1, you kind of know that u equals sine of x would be the nice substitution to do here. Your du would be that cosine of x dx. And so your integral I, you can actually rewrite that as just the integral of 1 over u times u minus 1 du. Right? So that's the first step. Now, again, this is a new integral. You go through the same process in your head. Does that look like a basic rule now? Right? Because sometimes you do a substitution and right away it looks like a basic rule, right? So, for example, if you had like the integral of x sine x squared dx. Doesn't look like a basic rule, but if I do u equals x squared, my du equals 2x dx. And so this integral would just become 1/2 sine u du. And you're like, that's a basic rule. In fact, that guy looks like the left side of rule 6, right? It looks exactly like a basic rule. Right? So now you just write down, what does the right side of rule 6 look like? Well, cosine plus c, right? And so everything is trying to do a basic rule. So sometimes you do a substitution and right away, it looks like a basic rule, but not always. So in this case, I do a substitution in hopes that it would look like a basic rule, but it doesn't quite look like a basic rule. So things aren't done. So now I start to think, all right, I did the substitution, didn't kill the problem. What else can I do? So now I know a bunch of other techniques. I know integration by parts. I know trig substitution. I know partial fractions. I know regular trig integrals. This isn't a trig integral, so obviously that's not going to work. Trig sub, also not going to work because I don't have one of the forms. The u isn't squared. And yeah, by parts, what do we do for the parts? So here you would like, oh, that's actually a rational function, and the denominator is factorable, and it's also proper. Therefore, partial fractions might be something I want to do. How does that work? Well, the parts would be based on the denominator of the original function. In this case, we can do the cover-up method because these are non-repeating linear factors. So cover up the u, plug in u equals 0. I would get a -1. Cover up the u equals -1, plug in 1, I get a +1. So those are the partial fractions. Now you think, does that look like a basic rule? 1 over u? Yes, right? Because you go to this chart, that looks like the left side of rule 3. And also, the 1 over u -1 also technically looks like the left side of rule 3. If you were to do like an extra substitution, you know, like a t equals u -1, then you would get the integral to look like 1 over t dt, right? So it also looks like that. But this is the kind of integral where I don't expect you to go through an extra substitution. I expect you to just see it. But if you don't see it, do an extra substitution. At the end of the day, you keep doing a technique until you get it to look like a basic rule. That's the whole point of all of these techniques, right? By doing partial fractions, it gets me to a point where I can apply a basic rule. And so here, the basic rule is this is ln, and this also be an ln. And because this was a substitution, I'm going to replace it. U was sine. So that's my antiderivative. Okay. So again, I see an integral. Where does it all start? With the basic rules. Where does it all end? Well, essentially also with the basic rules. The basic rules are everything, right? Everything we're doing is either applying a basic rule or trying to bring something to a point where we can apply a basic rule. All these techniques are just ways of doing that. How can I rewrite this thing so that it looks like one of these basic rules that I have, right? So it starts there and it ends there. So you're like, does this look like a basic rule? No. Can I simplify it algebraically? Just like divide something or expand something and make it look like a basic rule? No. Then you have to start thinking, oh, well, can a substitution work, right? In which this case, you know, through practice, you'll know what the good substitutions would be, and you would do that. If you are a little shaky on that, I would recommend go check out my Calc 1 lectures where you start substitution from scratch, and I talk about what a good substitution would be. What do you look for to make a good substitution? But I'm going to assume that you all know that because you all passed Calc 1 to get here. So then you start thinking substitution. Now, sometimes you do a substitution and everything is hunky-dory. That was Calc 1, essentially. You do a substitution one time and you're good. However, life is more complicated than that. Sometimes you do the substitution and you still end up with something that you can't apply a basic rule. So then you need something further, right? And that's where the other techniques come in. And you would choose a technique based on what you're looking at. So here, by parts, trig sub, none of those seem to work, but partial fractions works because it's a rational expression with the denominator factorable, and it's a proper rational expression. So that ends up finishing the job. Okay, so in the end, these are the things that should go through your mind. This is how you'd think about it, and in that order, right? So you don't, a good thing is going to be, and this is something we'll actually talk about tomorrow. Yeah, we're actually going to talk about that tomorrow. Like one of the red flags that you want to avoid is this idea of being stuck, where you look at a problem and you kind of like, I don't know where to start. Like that's not somewhere you want to be, right? When it comes to integration, you always know where to start and you always know what to think next, right? You want to be there, right? And at the end of the day, you want actually writing out the steps to be the easy part, right? Like no thinking happens while you're writing. The thinking happens before. You kind of know where this is going to end up. You know what steps to take to get there, right? That's where you kind of want to be, right? So I know I see an integral, I always think basic rule. Can I simplify it to be a basic rule? Would a substitution work? Always think those three things in that order every single time. That might help you solve the problem. If not, then you start thinking more sophisticated. By parts or trig substitution or partial fractions. And each of these have conditions that need to be fulfilled for them to work, right? So trig sub, you need one of those expressions like x squared minus a squared minus x squared plus a squared. Partial fractions, you need a rational function with that is proper. So it's a ratio of polynomials where the degree of the top is small, strictly smaller than the degree of the bottom, and the bottom factors. Then a partial fractions can work, right? Integration by parts, usually we remember the origin of integration by parts. It was undoing the product rule. So that's usually when you see a product of two things, and it works best when there are two different kinds of things. Like you see an exponential times a trig function, or a polynomial times an exponential. That's when you kind of think integration by parts. Integration by parts can work when you have two of the same thingies. Like that's what happened when we figured out the integral of secant cubed. Where did we figure that out? I don't even remember. There was a point where we figured out the integral of secant cubed. But essentially, the trick was to write that as secant squared times secant and then use by parts, right? But again, you would get to that point by realizing that nothing else we know could help, right? Because if you have secant cubed, partial fractions doesn't apply. Substitution doesn't apply. We actually tried substitution and it didn't work. Just straight up substitution. It's not a basic rule. Well, now it is, right? Now it's a basic rule. And you know, what were we left with? By parts was the only thing we were left with at that point. So sometimes it's like a process of elimination. But you shouldn't really be in a point where you're like, I don't really know what to do, right? That's not a great sign. And we'll actually talk about that tomorrow, I think. Because tomorrow, I think we're going to start with the last integration technique I want to teach you guys. And then I'll kind of summarize everything I'm saying. Like, how do you actually approach a problem? What do you think about first? What do you think about second? What do you think about third? You shouldn't ever really be lost, kind of. You should always kind of know what direction you should be thinking in. So let's move to this one. So I specified not using trig sub here because I believe we did do a problem like this using trig sub. In fact, I think this was one of the examples that we did with trig sub, but I specifically want you to try to avoid it in this case. Now, remember when we were doing trig sub, one of the things I mentioned is if you have an odd power either in the numerator or denominator, so like here you had this x cubed, then you don't need a trig sub. Some other kind of substitution would work. And we actually did, I want to say we did that example, or something super similar to it. No, well, example F was pretty similar. But yeah, so we do know that we can do something like this with trig sub, but here I specifically want you to not use a trig sub. So if I tell you this, that, hey, I don't want you to use a trig sub, how are you going to do that? Well, you would try a regular substitution, right? Because again, I see this, the first thing I'm going to think, is it a basic rule? Is it in that chart that Jhevon gave us? No. Can I simplify this to be a basic rule? No. Like, I have stuff under a radical, there's an x on the outside, I can't like divide x into each part. It's not gonna help. And so now you start to think, okay, substitution. And a good rule of thumb on what makes a good substitution is like, what makes this complicated? What makes it annoying? And this thing under the radical is what makes that annoying. The fact that there's a sum under the radical. If it were just an x squared under the radical, that simplifies very easily and it's a basic rule. And so a good substitution would be something that gets rid of the radical. So something like a u equals 1 plus x squared, right? Or even better, because I don't want radicals at all, I can make a u squared equals 1 plus x squared. So I make what's under the radical a square, so it gets rid of the radical. Awesome. So then now I know that u du is equal to x dx. And generally, I don't have an x dx, but I can put it in. Notice that this guy is I, which I can write it as 1 plus x squared over x squared times x dx. So I can multiply and divide by x to get my x dx in there. That's not going to be an issue. And so that's my x dx right here. And I can replace that now with u du. So now I'm going to go in. So what is my radical of 1 plus x squared? Well, that's just u, right? Because from this, I have those two facts. One, I know that u is equal to the radical of 1 plus x squared. I also know, by the way, that x squared is going to be 1 minus u squared. So wherever I see an x squared, I can replace it with 1 minus u squared minus 1. And wherever I see a u, I can replace it with 1 plus x squared, or vice versa. So the top gets replaced by u, the x squared gets replaced by u squared minus 1, and the x dx gets replaced by u du. So now my I is this integral. Okay. So I see this and I'm like, all right, it's not a basic rule, can't simplify it to a basic rule. And the 1 plus x squared might make me have that knee-jerk reaction and think trig sub, which technically shouldn't be the third thing I think about, but the moment you think trig sub, you should always second guess yourself. Wait, do we really need to do this, right? And the fact that there's an odd-powered factor of x elsewhere hints to you that no, I technically don't need a trig sub, right? A regular substitution can make this nicer. So I did a regular substitution and I get this. Now at this point, you're like, all right, I did my regular substitution. I get this integral. And it's actually still not a basic rule. However, I can apply partial fractions to this after simplifying a little bit. You know, you subtract your 1, you add 1. That becomes 1 plus 1 over u squared minus 1. That, of course, you can factor. And that, of course, you know, you'd split it into these two things. I can use the cover-up method to figure out what's the numerator of u minus 1. Cover up u minus 1 in the original, this one. Plug in u equals 1. because that would make u minus 1 equals 0. I would get positive a half as the answer. Similarly, cover up the u plus 1. Plug in u equals negative 1, which would make u plus 1 equals 0. I would get negative a half as the answer. So now this integral is really just this integral. And that integral is something that we know how to deal with very well. Because that's at this point, these are all basic rules. I mean, technically the last two terms are one step away from a basic rule, but that's good enough. Right. So you should be aware that for the last two, technically you want to do a substitution. You don't just jump into ln. I probably want to point that out earlier. I don't know if I want to make sure that that wasn't missed. I want you to appreciate, for example, in this example that we did a while ago, the 13/8 became 13/16. Hopefully you guys noticed that I changed the denominators here. And the 9/8 became 9/16. Where did the 16 come from? It's because I did a substitution in my head. U equals 2x minus 3. My du would be 2 dx, which would mean a half du gives me the dx. So there's a 1/2 factor. And so the denominator, the 8, gets multiplied by a 2, and that's why I made it 16. So, I mean, I didn't write out the substitution, but I did do a substitution. So again, anything that doesn't look directly like a basic rule, there is some process to go through. Like technically here, I would do like t equals u minus 1, but my du would be dt, so it'll just be ln of t, and so there's no factor, no coefficient other than 1, but just to keep that in mind. And at this point now, I can actually plug in my u. My u is the radical of 1 plus x squared. And that's the integral here. Any questions, comments, concerns? So do another one. All right. So again, we're going to go through the process. So I show up minding my own business, not trying to cause any trouble. This integral pops up in front of me and I have to deal with it. So what do? Well, I start thinking, is this a basic rule? No. Can I simplify this to look like a basic rule? I think I have all day, like I'm gonna divide this with long division and try to figure out what's going on. So probably not. Can a substitution work? Well, if a substitution could work, what would it be, right? So you're gonna think about this. And the denominator being the thing you want to substitute might make sense. So I'd probably think that, so I would go u equals x cubed plus 3x minus 4. My du would be 3x squared plus 3 dx. So can a substitution work? well, yeah, that's actually just 3 times x squared plus 1 dx. So 1/3 du is equal to this x squared plus 1 dx, which I have, that's right here. So this means that my integral is 1/3 the integral of 1 over u. Which is a basic rule. So actually, this one didn't require anything sophisticated at all. It was x cubed plus 3x minus 4. Yeah, so this was a regular substitution. So I don't know if anyone tried this and tried to do like a partial fractions or whatever. One thing that kind of makes you pause with the partial fractions thing is, remember that you have to be able to factor the denominator. Factoring a cubic generally isn't feasible. Like it's one of those things where it's hard to get to work out. So you might not want to actually go that route. But yeah, so here you didn't actually need anything. It's just a substitution. So sort of a trick question to keep you on your toes. If you're trying this and you tried anything more sophisticated, you're working and thinking way too hard. So yeah, that was just a regular substitution. This, I believe, is the last example. Yeah, gonna end tonight with a bang. So this one is actually going to be a situation where there's something I asked you to look up, rational roots theorem, right? So in this case, it's going to be something where we actually can factor the denominator. And the thing is, I wouldn't even think in that direction, except I first thought substitution and it didn't work out like the last time. So if I went in and was like u equals x cubed minus 2x minus 4. And so my du would be 3x squared minus 2 dx. And yeah, that doesn't work with this guy. Like here, I could like factor something out and I see the numerator. That isn't true anymore. Like the numerator doesn't look anything like that guy. It's not gonna be really nice. So it's like doesn't work. So at this point, you think of other things by parts, forget it. Trig sub, no, it doesn't work. It's a cubic in the denominator. So this would kind of be at a loss, except I did give you a hint that factor the denominator before starting. So now you're in a situation where I have to remind you how to factor a cubic that's not like an obvious factor by grouping or something like that. So let's actually work on factoring this guy and remind you of some things that you did learn in pre-calc, but it's probably been a while since you had to do anything like that by heart. By hand. So let's factor. So again, there's a strategy for factoring, right? First thing you look for is common factors. Second thing, if it's 2 terms, you look for difference of squares, difference of cubes, sum of cubes. If there are 3 things and it's a quadratic form, you try the AC method or one of those other methods for quadratics. If it's 4 or more terms, you try a factor by grouping. And if it's none of those, you try this little thing where it's like you apply the rational roots theorem with long division or synthetic division, but I prefer long division because synthetic division only works in a few cases. Long division is more general. And remember how the rational roots theorem works. Rational roots theorem says that if something has rational roots, meaning if it can factor and the zeros will all be fractions, then the zeros have to have a specific form. They have to be the coefficient of this term. It has to be one of the factors of this guy divided by one of the factors of the leading coefficient. So the factors of 4 is 1, 2, and 4, and the factors of the coefficient is just 1 plus or minus. So the possible roots can be so by the rational roots theorem, if, this is a big if, you don't know a priori, but if rational roots exist, they are of the form plus or minus factor of constant term divided by factor of leading coefficient. So by applying that, you know that the possible candidates are, so here, x equals plus or minus 1, plus or minus 2, or plus or minus 4 would actually be the candidates, right? So it's the factor of 4 divided by a factor of 1. So it's either going to be 1, 2, or 4 on the numerator, and it can only be 1 on the denominator. So you'll end up with these numbers. Now, what you want to do is you want to plug these into that polynomial to see which one gives you 0. So that means you're going to take each of these x values, or one of them, which you might be able to eyeball, plug into this one and see, can you get a 0? So you can start with the easiest one, is probably where you want to start with. So for example, like positive 1. If I plug in positive 1 for x, does this give me 0? Right? I would get 1 minus 2 minus 4. No. Negative 1, does that give me 0? No. What about positive 2? I would get 8 minus 4 minus 4. So that actually works. So notice that x equals 2 works. Because if I take 2 cubed minus 2 times 2 minus 4, I get 0. Right? So this is what we know from the rational roots theorem. So here, these are the possible rational roots. And you're going to try to plug each of those into that cubic to see if it's a 0. And notice that x equals 2 works. Now, there's another theorem that says if you plug in something and makes a polynomial 0, that means x minus that number has to be a factor, right? The thing has to factor in such a way that x minus 2 is one of the things. So that when you plug in x equals 2, it gives you 0, right? So x equals 2 works as a root. This means that x, the expression x minus 2 is a factor. And so what you can do with that now, you know that the x minus 2 must divide into this polynomial evenly. So this means you can just go in, take your x minus 2, and we're going to divide that into this cubic. X cubed plus 0x squared minus 2x minus 4. And because this is a factor, when you divide it, you should get a remainder of 0. So remember how we do this? You're going to take the first term, divide it into the first term. So you take x into x cubed, you get x squared multiply everybody, you get x cubed minus 2x squared, subtract, that would leave you with a 2x squared. Then you take the x into the 2x squared, you get plus 2x. Then you take the 2x, multiply everybody there, you would get 2x squared minus 4x. You subtract that. You have a minus 2x plus a 4x, you get positive 2x. You do it again. Take your x, divide into this 2x. You get plus 2. Take that plus 2, multiply everybody, you get 2x minus 4. Subtract. You have minus 4 minus a minus 4, you get 0, which you have to get 0 here. There's no remainder because this thing factors in such a way that x minus 2 is one of the guys that would get canceled if you divide by it. There's not going to be any remainder. So you definitely don't need a remainder. However, what this means then is that this means that our cubic x cubed minus 2x minus 4 is, remember, it's the quotient, which is x squared plus 2x plus 2. So this divided by x minus 2 is the quotient plus 0 over x minus 2. So you can actually ignore this part. And that actually tells you how to factor, because now if I multiply both sides by x equals x minus 2, I get that my x cubed minus 2x minus 4 equals so that actually factors into that, right? Which the process for actually doing that is a pre-calc problem, which it's another one of those things where it might take a while to write out, but the steps should be straightforward and you can get through it relatively quickly. But that's how you would factor something with the rational roots theorem that doesn't obviously factor by the simpler means. Anyway, in the end, we can now go with our integral. So this means that the integral I is going to be x squared minus x minus 2 divided by this whole thing. How does that help us? Well, I think the numerator also factors. And I want to say it's x minus 2 times x plus 1. So these guys cancel. And so this is just the integral of x plus 1 over x squared plus 2x plus 2. So my original integral simplifies like that. And now this is just a new integral, and I go through that whole thing in my head again. Is it a basic rule? Blah, blah. And you would realize that a substitution now would work. My x plus 1 dx is right there. So this means that my I is just equal to 1/2 the integral of 1 over u du. Yeah, and again, we don't need partial fractions or anything after that. The work in this one really happened here, trying to figure out how to factor this guy. Which, using the rational roots theorem, plugging in the, so you want to factor something where it's like, okay, it's not like a regular quadratic, and none of the factor by grouping or none of that works. You create expressions like this. And then one by one, you try to plug in so that you get 0. When you find something that gets 0, it means x minus that thing is a factor. So you can divide by it and get 0 as a remainder. And what that means is that this guy is going to be this guy times that guy. So once we have that, I can swap him in, and then it simplifies. And then at this point, I think of it as a whole new integral, and I go through my steps again. And that is the last example we have. Kind of ending right on time here. So that ends this section on partial fraction decomposition. So we have one more technique that I want to cover. Everything else in this course is either going to be an application of integrals or something not doing with integrals anyway. But in terms of the techniques you need to actually figure out an integral, there's only one more we want to learn, and we'll learn that tomorrow. As well as, I'll summarize kind of how you want to think about integrals. How do you approach doing an integral problem? So we'll actually wrap up there. I do know that someone wanted to have an office hour with me right after, so I guess you can stay in the room. I won't close it. But as for everyone else, I think I am going to say good night. So have a good night. I'll see you guys tomorrow. See you in the next one. So ciao.